Okay, this example is on the Laplace and Poisson equations. So, for example, two long concentric cylinders exist in free space. The inner cylinder has a radius of 1 centimeter and is grounded. The outer cylinder has a radius of 3 centimeters and is at 1.5 volts. So we're going to find A, the potential difference everywhere between the cylinders, and B, the electric field everywhere between the cylinders. For time purposes, I've already sketched a picture of this. You need to be able to come up with this picture, okay, or a similar picture, however you decide you want to orient the cylinders or whatever. So I'm choosing cylindrical coordinates and I'm orienting my cylinder along the z axis like I've shown here. So note, because the outer cylinder is at positive 1.5 volts, the electric field is going to point inward radially. So that's what I've shown here with electric field E there. Okay, so there's no charge distribution inside or in between the two cylinders. We're not told that, and we're told this thing is in free space, and so we can use Laplace equation. Laplace equation, del squared V equals 0, right? And again, I'm using cylindrical coordinates, so we need to consider what del squared, or the Laplacian operator, equals in cylindrical coordinates. Before we do that, let's consider how our electric field varies as we go along the three directions, or the three dimensions in cylindrical coordinates. So first there's the radial dimension, and so of course the electric field varies, or I guess we're talking about the potential difference for right now. Of course the potential difference varies radially, right? Because at 3 centimeters we're at 1.5 volts, and at 1 centimeter we're at 0 volts. So certainly it varies with the radius. Now the second direction is the phi direction, and so if we imagine we just rotate, right, phi, well, because of symmetry, if we walked along a phi, or if we just kind of just change the angle, right, then everything would look the same to us. We would still be the same distance away from 1.5 volts and the same distance away from 0 volts, and so nothing changes with the phi direction. And we're also told that these cylinders are long, or we can think of them as infinitely long compared to 1 centimeter and 3 centimeters. And so if we walk along the z-axis, then we're no closer in getting to the end, if that's the case. And so nothing varies in the z direction. Everything looks the same that way. So all we have is variation along the rho direction. And so then the Laplacian operator becomes 1 over rho d rho, then times rho d, and then v d rho, like this. So this is not something you need to memorize. Have it on your note card, or bunny ear it in your textbook. But this was covered in the Laplacian section in the vector calculus videos and so forth. Okay, so now we've got to figure out what is this going to equal, or what is v here. We need to solve this differential equation. So if I can multiply by rho on both sides, and still then I would have equal to 0. And so essentially I have the derivative of the thing in parentheses is equal to 0. That means the thing in parentheses has to be equal to a constant. That is to say, rho dv d rho must be a constant. I'm going to call that constant C1. You see, because if the thing in parentheses is a constant, then when I take its derivative, I get 0, and then when I multiply by 1 over rho, I still have 0. Alright, so now I can certainly divide by rho. So this is 1 over rho times C1. So now I've got the derivative of v with respect to rho is 1 over rho c1, and so I integrate again, so this is integrating a second time, and I get v is equal to then c1 times the natural log of rho, because the integral of 1 over rho is the natural log of rho, and then plus a new constant of integration, c2. So this is the general, I shouldn't say general, this is the unspecified solution to the Laplace equation in cylindrical form. So now I need to apply the boundary conditions. So this is a function of rho, and if I put in 1 for rho, and I'll just keep in mind that that rho is in centimeters, but if I put in 1 for rho, I should get 0 volts, right? Because that inner cylinder is held at ground. So if I put in 1, I should get 0 out. So this means that C1 times the natural log of 1 plus C2 is equal to 0. And then what is the natural log of 1? Well, that's 0, and so this implies then that C2 is also equal to 0. So we're closer in specifying our solution. We've got C2. Let's apply the other boundary condition, and so when I plug in 3 for rho, I would have C1 times the natural log of 3 plus C2. C2 is 0, we just found out, and that must be 1.5 volts. Okay, so I solved this for C1, and I quickly learn that C1 is 1.5 divided by the natural log of 3. Right? So now I can completely specify the solution to the Laplace equation, right? And this is V equals 1.5 times, or 1.5 divided by the natural log of 3 times the natural log of rho plus 0. So that's my solution, and so this is in volts, and I will just keep in mind, I'll just write a note that rho is in centimeters, right? Just keep that in mind. So that's what I've got there. So we know that the outer cylinder is at 1.5 volts and the inner cylinder is at 0 volts. So how does it change? Well, it changes according to this expression. So what we can do is we can kind of graph that change. This is called the profile, the voltage profile, or the potential difference profile. And so and I'm just graphing this equation simply. So at 1 centimeter, right, the natural log of 1 is 0, and so I have 0 volts. That's good because I know that at one unit away, I should be at 0 or ground. And then if I plug in 3, I have the natural log of 3 over the natural log of 3, which cancels, times 1.5, so I know that I'm at 1.5 volts. And if you're familiar with the natural log function, this thing looks like this. Okay, so this is the voltage profile then as I go from 1 centimeter to 3 centimeters away. This is how the voltage changes as I do that, and so that's the answer to part A. All right, so now we're going to move on and get the answer to B. So I want to know what the electric field is now everywhere between the cylinders. So I have to recall, how is the electric field related to the voltage? And we should remember that the electric field is the opposite, or the negative gradient of the voltage. So we have then, because the voltage only varies with rho, then this is simply a negative dV d rho times a rho, like this, right? And so this means with v equal to this guy, and we take the derivative of rho, and that's 1, or we take the derivative of natural log, everything else is a constant, so the derivative of natural log of rho is 1 over rho, right? And so we've got negative 1.5 over natural log of 3, there's our constant, times 1 over rho, that comes from the differentiation, and then I've got the a rho direction, and this was in volts per centimeter. Okay, so we can change that to negative 150 over the natural log of 3 times 1 over rho in the rho direction, volts per meter. And that is the answer there.